It's everywhere around us, but do you understand it? Today we're going to talk about pressure, density, and the buoyancy force, and do a few practice problems for each of them. Perfect.
Now, we hear about pressure all the time in our daily lives. But what actually is pressure? In physics, pressure is defined as force over a given area, and it's usually given in pascals or newtons over meter squared. Now, I like to think of pressure as like force given dimension. So, for example, if we take this wombat here and we imagine he's standing on like a square, and that square is on a table, I suppose. This is a table. Sorry, I'm not the best artist. This wombat has a certain weight, right? Because he has a weight, gravity is pushing down on him, and that means that there's a force, the force of gravity coming down, and it's going to be given in newtons, right? Now, this area, the square that he's standing on, that's where the force is like distributed through, and we're going to assume that the force is distributed equally. And so, in order to calculate the pressure that the wombat is exerting on the table, we would need to know the dimensions of the square and the dimensions of the wombat. So, for example, if the wombat is like 12 kilograms, I think that's a big wombat. I haven't met very many wombats. 12 kilograms, we can say that times the force times the acceleration from gravity, that's going to be about 120 newtons going down, right? And then let's say that this box is 3 meters by 4 meters. That would give us an area of 12 meters squared. How convenient. So let's take it and plug these two numbers into our formula. So if we have pressure equals force, which is 120 newtons, over 12 meters squared, that's going to give us a pressure of 10 pascals. Simple as that, right? We got pressure. Moving on. The other thing we need to learn before we move on from pressure is gauge pressure. Now, on any given day, you got your sun and you got the atmosphere. And the atmosphere, believe it or not, has weight because it's made out of like water vapor and all this stuff. And all of that exerts a force downwards from the force of gravity. And we just learned that pressure is equal to force over area. And because of that, the atmosphere actually constantly exerts a pressure downwards on you. And this is called the atmospheric pressure, usually abbreviated as ATM. It's equal to about 101.325 pascals at sea level, or 101.3 kilopascals, which is just 1,000 pascals. And the reason we need to know this for gauge pressure is that gauge pressure is equal to the difference between the total pressure of something, of a system, minus the surrounding atmospheric pressure. Let's do an example to understand. Right here, we have a very awesome can of soda. Yes, it's very cool. Okay, in this can of soda, it's carbonated. It's like you got that Coca-Cola inside of it. And so that Coca-Cola has a pressure to it, right? Usually, let's say like around 3 atmospheres. And this nice, delicious can of soda is sitting on like a beach somewhere in California, right at sea level. And so that means that there's 1 atmosphere outside. In order to calculate the gauge pressure, like between like this part or something, we need to put it into our equation. And so we just said that the gauge pressure is equal to the pressure of the thing minus the atmospheric pressure. And so that means that in this case, we have 3 atmospheres of pressure inside this can of soda. So that's 3 and 1 atmosphere outside. And that's going to be equal to a gauge pressure of 2 atmospheres. Now that we understand pressure, we're going to play a little game called Pop That Wombat. My dear wombat friend, it's time for you to go. Unfortunately, Mr. Willie the Wombat here, that's his name now, needs to die. And part of that is we're trying to figure out what gauge pressure between like the inside of Willie and the external air he's able to sustain before exploding. So we know that the outside is about 1 atmosphere, right? Because he's in San Diego or whatever, and he's by the ocean. He's very chilling. And according to an article I read, human lungs can sustain about like 40 kilopascals of overpressure before they explode. And so Willie here, he's actually really buff. Like, look at those muscles. Those are terrible muscles. But look at his muscles. He's a strong guy. So maybe he's able to sustain just a bit more, like 50 kilopascals of overburden. And so let's start setting up our equation. We know that the difference between the atmosphere around him and the total pressure inside is 50 kilopascals, right? And so that's going to be our gauge pressure. And that's going to be equal to his internal pressure minus the 1 atmosphere outside. And we know that 1 atmosphere is equal to 101.3 kilopascals, right? And so, just using some simple algebra, we're able to like rearrange that. And then we know that the total pressure inside the wombat needs to be 151.3 kilopascals. And then he explodes. Oh no, Willie, I'm so sorry. But yeah, that's pressure, and now we understand it, and now we can start doing cool things like going deep in the water with submarines and understanding why we're able to like breathe and why we're able to drink milkshakes through a straw and all this fun stuff. Now the second thing we need to understand is density. And the reason why this soap bottle is so freaking cool is, of course, because it has 2 parts, right? There's this cool looking blue part, and it's like clear and all that, and then there's this white part, and it's like so awesome. I know, it's really cool. Ooh, ah. Anyways, and the reason these 2 parts are separate and remain separate is in part because of density. And density in physics is represented with this thing. You might be asking, isn't density a D word? And don't we already have pressure in this unit, which is a very important P word? Yes, we do. I don't know why they chose this very similar looking Greek letter to represent density, but they did. And so now we have our beloved friend, rho. And he's going to represent density, and that's mass over volume. So if you want a greater density, you increase the mass and decrease the volume. And if you want a lower density, you do less mass for more volume. And this is why the blue part is on top of the white part, probably because the mass per volume ratio of the blue part is much lower than that of the white part. And this plays an important role in another concept called the buoyancy force. Put peanut butter in water, it doesn't float. Shoot. The peanut butter floats! That's why when you put a tomato in water, it doesn't float. That's why when you put a rock in water, it does not float. Evidently, peanut butter and tomatoes do not sink. That's because despite the force of gravity pushing down, there's a counteractive force, the buoyancy force, that pushes upwards. Now, what causes this force? In a liquid, this force is everywhere. This is all matter, and it's all unfixed, so there's constant tension within a liquid. Most importantly, there's constantly pressure coming from the top. The weight of the water, the weight of the mass of the water pushing down on the water beneath it. And that creates pressure. Actually, we have an equation for this. That's pressure equals the density of whatever liquid times gravity times height, or the depth of the water. And so because of this equation, we know that at the top there's relatively little pressure, and at the bottom there's a lot of pressure. This is a pressure difference. And this is a reason why we have a buoyancy force. Things like to go from high pressure to low pressure situations. And so there's constantly a force going upwards towards that low pressure situation. And this is counteracting the force of gravity. Normally in a liquid, because the density is equal to all the other things, it kind of balances. And force of gravity and force of buoyancy balance out, and water doesn't move normally, like it can stay still. But if we take something like a tomato and put it where that water would be, now that's a different story, because the density of the tomato is different. And this is how we begin to calculate the buoyancy force. That's FB equals density times V times G. It depends on the volume of the thing, the amount of water we're displacing, because that's how much area is going to be tried to fill, the water is going to try to fill, and that determines how powerful the buoyancy force is. In cases like the rock, the mass of the rock simply outweighs the volume that it takes up. And so the density is much greater than the density of water, and it sinks. All right, you got that? Everything good? So now we have a pretty good understanding of how pressure works, how gauge pressure works, how to calculate different densities and what to use them for, and finally, buoyancy force. All right, you guys ready for some fun? It's Jeopardy time. Welcome, ladies and gentlemen, to tonight's episode of Jude's Jeopardy. I'm your host, Jude the Dude, and we're about to learn some physics. Alrighty,
First question is pressure 200.
This is Jeopardy! How much pressure is exerted by a column of water that is 3 meters deep? Use density of water equals 1,000 kilograms per meters cubed, and G equals 9.8 meters per second squared.
The answer, what is 29,400 pascals? I hope you got that one right. All you needed to do was use that pressure equation from earlier. P equals rho times G times H, and plug in the values. Very nice. Hopefully you'll get this next one too. And that is gauge pressure for 400.
The Wombat 9000 pressure simulator shows the animal is under an internal absolute pressure of 160 kilopascals. What is a gauge pressure, and is the combat wombat in danger if its max safe gauge pressure is 50 kilopascals?
Ladies and gentlemen, drum roll please. The answer, of course, yes. This wombat is under 58.7 kilopascals of overpressure. He might explode. The next one on the chopping block is density 300.
This 1 liter bottle filled with mercury, density equals about 13.6 grams per centimeter cubed, is heavier than the same volume of water because of this property.
What is higher density? Yep, that's right. You put more mass into the same amount of volume, it's going to be heavier. Next up is buoyancy.
An object displaces 0.01 meters cubed of water. Given water's density is 1,000 kilograms per meter cubed, this is a buoyant force acting on it. Use G equals 9.8 meters per second squared.
For this one, we just needed to use our trusty equation, buoyancy force equals density times volume times gravity, and we get an answer of 98 newtons. The next one, and final one, is miscellaneous for 500.
A cube weighs 100 newtons and floats with exactly half its volume submerged. This is the density of the fluid it's floating in if the cube's volume is 0.02 meters cubed.
For all the marbles, this one comes out to be, what is 1,000 kilograms per meters cubed? Or if you got 1024, that's also okay. Again, we use the buoyancy equation. Force of buoyancy equals density times volume times gravity. And by rearranging to solve for density, we get our answer. Thank you so much for watching, ladies and gentlemen, and have a good night.